who are desperate to get wireless, if you go to the town, there are lots of places with free Wi-Fi, etc. It's a bit of time, but if you really need it, it's there. So let me finish what we didn't have time to talk about last time. We talked about the atomic collapse problem and how charge impurities on graphene are used to model it, and the idea is that even if one charge impurity is subcritical, you can bring them together by using some STM manipulation magic and produce something like artificial nuclei with compound nuclei with large charge. And this experiment can go as large as 5, and then these charges start repelling each other, and these clusters are not stable anymore. But that's enough to, because on graphene fine structure constant is a order 1, it's enough to go through the transition and see formation of resonances, and so we discussed that last time. Right, and then there is a question about whether there is any symmetry change at this transition, and I would like to argue that it's scaling symmetry that breaks at this transition in an anomalous way. So there's no spontaneous symmetry breaking, but it's just that scaling symmetry in its pure mathematical form assumes that we have the entire range of length scales available from the smallest to the largest, and in that case, as we discussed, we can use scaling symmetry and derive, draw conclusions from it, prove theorems, etc. And in the Dirac-Kepler problem, we always have, as in any other physics problem, we always have a regularization, which in this case will be on a lattice scale, or if you have a charge impurity which is positioned some distance away from the graphene plane, it will be the distance to the charge impurity. So there is always some short-range regularization, which we usually ignore. We write kinetic energy by expanding the Bloch bands near the Dirac cone, ignoring high energy states and low energy states, and get this gradient operator. Similarly, we take the Coulomb potential, which at short distances doesn't look like 1 over r, but we ignore that, and in a long wavelength limit we write down this problem, and then in the long wavelength limit it acquires scaling symmetry. You can rescale distances and energies, and you get back the same problem, and that's an exact symmetry of this Hamiltonian, of course, provided that low energy properties are not sensitive to UV regularization, right? And well, of course, if it's an exact problem, if it's an exact symmetry, you can draw conclusions from it the same way as when we prove Pythagoras theorem. You can say that there's no energy scale you can construct because of the scale invariance, and because of that, there cannot be any energy dependence in any dimensionless observable, like scattering phase, which is dimensionless, can't depend on energy, because it could only depend on energy via some function of energy divided by units of energy. But in this problem, we don't have units of energy, so scattering phases should be constant, and then from that, for all dimensional quantities, you can similarly argue what their dependence on energy should be, and so for Fermi energy, conductivity will scale as Fermi energy squared, etc. So, and then if scaling symmetry is a good symmetry in the low energy limit, then we cannot have resonance and we cannot have collapse. So collapse by just the presence of collapse means that scaling symmetry is is broken, and it's something that is rather well known in many areas of physics, in particular, and very important in high energy physics, where there are various kinds of anomalies that manifest in the fact that when you have a field theory which requires UV regularization, every field theory is like that. When you introduce a regularization, then the theory with anomaly changes behavior not only at the UV energy scale, but over the entire energy range from large to smallest scales. And there are also simple, one particle quantum mechanics examples of the same nature. For example, if you take a 1D Schrödinger equation for a massive particle with negative 1 over r square potential, then here I can make the same argument that scaling symmetry is an exact symmetry of this Hamiltonian, same way as before, because kinetic energy scaled as gradient squared, and this is 1 over r squared. So here we have scaling symmetry, and therefore we cannot have any energy dependence of scattering phase, any bound states, provided scaling symmetry is an exact symmetry. But as is well known for alpha, which is smaller than the critical value, which I think is -1/4, something like that, we get bound states. So we get scaling symmetry unbroken. And then here it's broken, and so this is the collapse regime in this problem. This problem is quite interesting. It's been studied by many people, because it turns out that if you look at this subcritical regime, then in addition to scaling symmetry, which is manifest from the Hamiltonian, there are also hidden symmetries, and in fact there are two other independent symmetry generators which, combined with scaling symmetry, make the actual symmetry SL to R, and then so that's conformal symmetry that is exact for subcritical state, and then becomes broken in a supercritical state, and you get bound states and whatnot, and sensitivity to regularization. So this is another example where there is a symmetry change, even more more profound than in this case, symmetry change at this transition when we acquire sensitivity to regularization. Any questions?
Yeah. I don't think it's an example of anomaly, right? Because anomalies don't depend on interaction. It's kind of strange that you just change the coupling constantly.
Well, that's in field theory. So that's okay. I mean, we can discuss what is anomaly, what isn't anomaly. In field theory, there is always an interest in effect of regularization, and in particular in limit of weak coupling. But I think the sensitivity to regularization, or absence of it, is the key in the anomaly. And then we can, the knob which we're varying may be interaction, or maybe dimensionality, or maybe something else, and in some natural sense, I think this is an anomaly.
Are you saying you have to regulate this? Quantum mechanics usually don't need to regulate.
Yeah, so in this case, you have to, because if you try to work on this operator with alpha more negative than -1/4, you will find, exactly as Dirac found in 1929, that Dirac operator is non-Hermitian without suitable regularization. And when you introduce regularization, have to do something about the singularity, or impose some boundary condition at finite distance from the origin, or something like that. So it's not, no meaning without regularization. That's right. Yeah. Yeah, you can, I mean, you can just try to construct, WTB solution, and you see that there is WTB solution with phase which increases indefinitely going to r equals 0, and it will wind infinitely many times, and it will be analogous to particle falling on the center. So, it's very similar, actually. Yeah, anyway, so that's, I should move on. So anyway, so I said all of that, global effect, and so this is a comparison with field theory anomalies. We get global effect at all energy scales, and we get bound state formation, as for example in this problem which was discussed by people in 1980s in the context of trying to invent alternative models for quark confinement. And the idea was basically to use this atomic collapse for massless fermions in 3+1 dimension, modeling quarks, and then in the supercritical regime, the resonances that we discussed can also be shown to exist for in the many fermion problem, when you have not instead of 1 Coulomb potential which is stationary and then fermion moving around it, you can take fermions which are mobile and argue that similar resonances that occur in the supercritical case can be potentially related to phenomena that to quark confinement, basically. And so this, this may or may not be a correct explanation of quark confinement. People you can find various opinions on that in the literature. However, it's a perfectly valid extension of what we discussed for static Coulomb charge to field theory, and in that sense, what we discussed provides some, condensed matter high energy physical connection. Yes?
This is the collapse of one fermion, but if we have like 2 or 3 fermions,
that's right.
Since we're talking about orbits, that problem is chaotic in the classical sense. Will it be easier to collapse in that case? Like in the 2 fermion, if we have 2 fermions?
Yeah, so that's what they argued. So Gribov, famous particle theorist, wrote a series of papers going from 1 fermion problem, 2 fermion problem, and then many fermion problem. I don't want to review that, because it's all in the archive. In the 80s, he worked on this idea, basically did what you said. Right. So then, going back to my problem, so in our case, we have a knob which is coupling constant or the nuclear charge value, and so it makes it kind of somewhat more interesting than in high energy physics, because you can tune coupling and go. So just like in this one particle problem, in our case, you can go from subcritical case where scaling symmetry is exact and low energy limit and behavior is regularization insensitive, to supercritical case where scaling symmetry is broken over entire range of energies and you get sensitivity to regularization. So this is an example for some observables. You can take exact solution of Dirac equation in terms of hypergeometric functions and calculate, let's say, scattering phases, and you see that in a subcritical case there is no energy dependence. This is log scale in wave number and also in energy, and there is no energy dependence scattering phase in subcritical regime, and then in supercritical regime you get these kinks, and each kink has a size of pi and represents a resonance. And then this translates into behavior of other observables. For example, if you take transport cross-section, then in the subcritical regime, it will be a smooth function of coupling with no oscillations. And then as soon as you cross 0.5, which is the critical value for beta again is E squared over HV fine structure constant times z, nuclear charge. Then you start seeing oscillations, etc. Okay, so I tried make my case that there is something about symmetry breaking here. It was mostly verbal. I just rephrased everything we said yesterday, but in that maybe slightly more fancy language. Question is, can we really probe it, and can we demonstrate that give some example of scaling symmetry or its absence doing something physical? And so this is an example that I invented for this presentation. You can take magnetic field and add it to the Hamiltonian and ask how energy levels behave as a function of magnetic field. And so now, if we have scaling symmetry, then because of magnetic field, we have energy scale. Energy scale will be the Landau level spacing. And there is no other, important is that there is no other energy scale you can construct. And because of that, you can argue that every observable should be a function of energy divided by this energy scale. And that means in particular that if I look at the energy levels, they will scale with B as square root of B. B is convenient as a knob because as soon as you introduce B, continuous spectrum turns into discrete spectrum. Landau levels basically deformed by the presence of 1/r potential. And so we expect to see this kind of scaling when scaling symmetry is present, and something else when it's not present. And you can test it very easily in simulation. So this is a sanity check, basically. I take Coulomb potential with zero charge. And so in this case, I expect to see the Landau levels that we calculated last week, and indeed I do. However, in the simulation, there is a regularization built in. I diagonalize Dirac operator in which derivative is a difference. Can't do it otherwise on the computer. So there is a UV regularization built in. However, the energy scale for this regularization is much larger than what we are looking at. It may be 10 times larger in this case. And so you see that at energies which are 10 times smaller than UV regularization scale, you have a very good scaling of all energy levels with square root of B, and even values match Landau levels, so the simulation is working. Now, if you add Coulomb potential, you see that the energy levels no longer energy levels are shifted. They don't obey Landau levels formula. However, because of the scaling symmetry argument, they still scale as square root of B, and so that's in the case when my charge is only 80% smaller than the critical value. And I also should mention that the same discussion as we're having now would apply if I switch from non-interacting problem to interacting problem. If I add electron-electron interactions, which we'll do shortly, the Hamiltonian that we'll write will still obey scaling symmetry. So everything we're saying scaling symmetry-wise should be true also in the presence of interactions. So someone inevitably will ask me what happens to atomic collapse if you add electron-electron interactions, and so on the symmetry level. It's insensitive, so because Coulomb interactions have the same scaling properties as this Hamiltonian, and maybe there will be a change in screening or change in the threshold value, but nothing beyond that. Yes?
There's something that puzzles me in your second part, because when you have impurity, you break translational symmetry, so
that's right.
I expect a broadening of Landau levels, but
oh, that's right. Sorry, I forgot to say what exactly. So with impurity we have broken translational symmetry, but we have circular symmetry, we have angular momentum quantum number. So I take angular momentum, different angular momentum channels will show Landau levels which are, shifted in different ways. However, what's interesting from this point of view is to take the angular momentum channel where states are most sensitive to collapse, which correspond to wave functions sitting right on top of Coulomb impurity. If I take high angular momentum, then the wave function will be far away from Coulomb potential, and then it will look like this with small distortions, and this collapse behavior that you'll see on the next slide will not occur. It only occurs in one angular momentum channel near the threshold, and yeah.
Another question, it strikes also is, what happens is that the zero energy Landau level, for z equal to 0, shifts to low energies. Can you comment on that? Is it just a calculation here for one particular value? Is it the parity anomaly that you see here? Or?
Yeah, okay, so no, I think it will, the zeroth Landau level will shift proportionally, it will shift up or down depending on whether Coulomb potential is repulsive or attractive. So I think here I'm using attractive potential of a fairly high value, so this level becomes this level.
So you break particle Hall symmetry by the Coulomb. That's what it
yeah.
Means, it's not by keeping inversion symmetry intact.
That's right. So perhaps for the other value it will.
Yeah. So is it value symmetric, anti-symmetric in this case?
So for the other value, kinetic energy will have a minus sign in front, right? So we should see potential won't change with kinetic energy. So no, but because the shift is determined by potential energy sign, perhaps it will be the same for the other valley. Kinetic energy wouldn't. If I go to the other valley, basically these levels will switch, but we won't see that because they are particle Hall symmetric. And then when we add attractive potential, the zero energy level will probably still go down.
Okay, so in this case it's not
Yeah.
parity anomaly, it's just
Yeah. So anyway, I started talking about interactions because people actually tried to test these things experimentally to see whether, people did spectroscopy, various people, this is, soon after graphene was introduced, people looked at how Landau levels, whether Landau levels depend on electron-electron interactions, and they found, what they typically found, this is just one example from Columbia paper, but there are also paper from measurement in Grenoble by Potemsky, and then in San Diego by Basov and someone else. But basically what people find typically doing spectroscopy between Landau levels or something else is that scaling is obeyed, square root B scaling is obeyed, the slope changes. So there are these shifts which are small but observable, and that means that we are in, even with interactions, we have scaling symmetry. Right. Anyway, but then go back to my simulation. My simulation, if you now go make it over supercritical, then square root B scaling doesn't hold anymore, and you get clear deviations from square root B behavior. And so what it means is that we can use, in principle, magnetic field as a knob to study the relation between collapse and scaling symmetry breaking. One can do spectroscopy of Landau levels near charge impurity, and if it's subcritical, there will be a square root B dependence for all energy levels, and supercritical, it will break. Right. So B field can be used as a knob to study the relation between scaling symmetry and collapse. Okay, so I think I am mostly done with collapse. There is some additional topic that I can talk about if there is interest, so I can go on to interactions. Yeah?
I thought with STM there was some experimental realization related to collapse by the Chromie group, I guess, but I don't remember what it was. Do you have any comment on that?
Yeah, so that's sure. So that's what, of course, they.
Oh, sorry, I missed it. All right.
Right. Yeah. So this is Chromie. This is collapse. So yeah. So what they do indeed they listened to what we said and actually invented a way to model it with STM by putting charge impurities on graphene and then bringing them together to form charge clusters, and then by increasing the number of charge impurities in a cluster, you can gradually increase Z and cross critical threshold, and then you see resonances appear as predicted.
What would be the advantage of looking at the magnetic field experiment over what's already been done by the scaling?
Yeah. So magnetic field, I think, is a clear knob to test scaling symmetry. I mean, here, we know that there is scaling symmetry breaking. We can show it on paper, but in their experiments, there isn't a clear knob to address that. And if we do spectroscopy with magnetic field, then we'll see energy level that scales the square root of B in a subcritical regime and energy level that doesn't in the supercritical regime. So it will be a very clear demonstration of relation between collapse and scaling symmetry breaking. They unfortunately don't have magnetic field in their system, but other people do.
Regarding actually the scale that is introduced by the magnetic field, so in the plot you've shown, there is clearly a magnetic length at which scaling is somehow, well, there are two regimes in terms of magnetic field.
Yeah.
So can we predict basically the magnetic field at which this this avoided crossing appears,
yeah, so I think
depend on the high energy cutoff that you introduce in the model?
Yeah, I think this avoided. Yeah, no, good. That if we want to look at, if we want to try to interpret this, my intuition is that this thing probably corresponds to the energy at which you see resonance in the absence of magnetic field. And then if you turn on magnetic field, it turns into avoided crossing between lambda levels. What?
This is like anti-crossing.
That's right. Yeah. It's very typical anti-crossing because you see that not only it's an avoided crossing here, but also all these levels switch. This one goes here, and then this one goes here, and this one goes there. So they do this. Right. That's right. What? Yeah. Okay. Right. Okay. So.
Question.
Yeah.
How much does the curvature of the graphene sample affect the scaling of the real? Because the curvature leads to a pseudomagnetic field.
Right.
How much does it affect this scaling?
Yeah. So this, pseudomagnetic field is as good. Well, first of all, let me explain what was the comment. If you strain graphene, then there is a pseudomagnetic field generated by strain. Homogeneous strain generates something like a magnetic vector potential individually in each valley, and then inhomogeneous strain generates magnetic field, and generates a gauge field coupled to quasi-particles in the same way as magnetic vector potential, except that it has opposite sign in different valleys. So it's called pseudomagnetic field because of that reason. So one could pose a question, and actually part of this discussion, can we use strain, a pseudomagnetic field due to strain, to tune collapse and probe it, and potentially it's possible because magnetic fields due to strain can be can be non-zero and in fact can be very high, higher than fields achievable in the lab. However, I think at the moment the control over fields generated by strain is not ideal. Basically, people don't know how to tune it. I mean, you can find a bubble and then do STM on a bubble and see that strain field on a bubble is very strong and it distorts electron levels as magnetic field of some strength, but there's no way to like blow the bubble up or do something with the bubble, and so we have no knob. I mean, I'm sure that a couple of years it will be invented, but at the moment there is no knob to tune the strain field. Yeah. Okay, so I need to move on. Let me just flash, maybe, since there was this question, we thought about if we can access collapse in some other ways, and maybe let me just show you one thing. There was a long debate about the threshold for collapse if you vary nuclear charge, and then there are these experiments with compound with clusters made of charged impurities that we talked about. One can also ask a question: what if you introduce an Aharonov-Bohm flux? An Aharonov-Bohm flux is of interest because presence of Aharonov-Bohm flux on top of charge impurity does not affect scaling symmetry. You still get scaling symmetry in your Hamiltonian, and you can also realize Aharonov-Bohm flux in a number of ways. In particular, if you take graphene and find dislocation in it, then dislocation, there will be a strain field around dislocation, and just like you said, the strain field will produce some Zuda magnetic vector potential that will correspond to some Aharonov-Bohm flux value, which is purely geometric, and one can evaluate it, using Burger's vector with dislocation, and show that it's equal to plus or minus a third over flux quantum. Also, if you take Abrikosov lattice in a superconductor, each flux tube carries superconducting flux quantum, which is 1/2 of normal flux quantum. So, if you imagine a hybrid system where you have superconducting layer with magnetic field penetrating through it through flux tubes, and then graphene on top, then graphene electrons will see, if graphene is in proximity, it will see magnetic flux values which are 1/2 of flux quantum. And so that, if you think more carefully about implementation, in both cases there are difficulties, but at least this is justification to consider this problem on a piece of paper, which is very easy to do. So if you take Dirac Hamiltonian with Aharonov-Bohm flux quantum with some arbitrary flux phi, then you find several interesting things. So in this model, we take flux line, infinitesimally thin flux line with magnetic field being a delta function concentrated in a flux tube, and threading graphene right through where charge impurity is positioned, and then you find that the threshold for collapse is suppressed by magnetic field, by the presence of the flux, in fact it reaches zero when you reach flux which is equal to flux quantum. So these two realizations that give flux 1/3 and 2/3. Sorry, I said minus a third. I meant 1/3 and 2/3 for dislocations of different types, and then 1/2 for superconducting vortex. They correspond to values of flux which are either critical or near critical, even for weak contractions. So with this, in this way, one can in principle push the threshold for collapse down to very low values or even zero value, And then that creates something like a bicritical point where you have collapse boundary going through zero coupling, and then not surprisingly, you can treat exactly that bicritical point, and then from this exact solution you can get a very simple picture, for example, for what happens to screening. And the screening changes when you cross collapse threshold. I haven't talked about it, but screening changes in a kind of dramatic way when you go from non-collapsing state to collapsing state, and you can do it all in this, work it out very easily in this problem. And maybe I shouldn't talk about it. Anyway, whoever is interested, it's somewhat technical, and there is some algebra involved, and you can have the right integral equation for screening and solve it. But amazingly, near this bicritical point, one can write an exact solution and derive a power law. So what you find, maybe the answer is more important than derivation. You find that the screen potential seen by electrons changes from 1 over r to a power law potential. And you can compute the exponent in the weak coupling limit. Yeah.
In this situation, does finding the exact solution rely on any particular property of the system?
So it's scaling symmetry mostly, and weak coupling. So in the weak coupling, you can do analysis by you can do a self-consistent analysis of screening cloud at weak coupling, and then using scaling symmetry, the resulting integral equation that you get for screening charge can be Mellin transformed to a algebraically solvable equation.
So is it just in the vicinity of half flux, or is it is this analysis doable in the vicinity of half flux?
So this is something that people discussed but haven't really found an exactly solvable case. The issue is the following: that if you take, let's see, where is it? Maybe here. So if you take charge impurity and ask how the screening cloud looks, you can compute it at weak coupling. And what you find at weak coupling, and we'll see that when we switch to interactions, and we'll do it in some detail. At weak coupling, the screening cloud is like in a dielectric, meaning that if you put a point charge in a dielectric, this screen charge will be 1 over r, but diminished in magnitude. And that means that the screening cloud in a dielectric looks like a delta function sitting on top of that same charge, right? So this is what happens in graphene in a subcritical regime. If you take undoped graphene, put charge impurity in it, compute screening cloud, you find that it's a delta function, and it's not surprising because delta function in 2 dimensions is has the same scaling dimension as charge density. So based on scaling, you would predict delta function, and sure, if you do calculation, you get a delta function for screening cloud. But then when you go to the supercritical case, it should change because we break scaling symmetry, and so there should be some other form of screening cloud. And there was a debate in the literature about what happens to screening, etc. And there is no satisfactory treatment of this problem. As far as I'm concerned, but what one can do is invent this, somewhat artificial case when you introduce Aronoff-Bohm flux and then bring the threshold for collapse down to 0, and then at this point you can exactly solve Dirac equation. Well, let me maybe just say very quickly how this works. So at half-flux quantum point, you can exactly solve Dirac equation not only in one of our potential, but in any potential. There is one angular momentum channel where you can exactly solve Dirac equation.
What's
and then
the mathematical property that makes it possible? I mean, it looks really magical.
it factors. I'm not sure what's the mathematical property, but it simply factors into two one-dimensional first-order differential equations. You can solve them, and then you can write down scattering phase in terms of potential for arbitrary potential, and then using scattering phase, you can compute using Friedel sum rule. You can compute screening charge as a function of position without assuming that your potential is 1 over r. You can say that there is some v of r, and we compute scattering phase, and then compute charge through that scattering phase, and then get its relation with the potential, and then make it self-consistent, and say that's the Coulomb potential of that charge produces correction that gives that potential, and that gives the screening problem that can be solved. And then from that you get a screening cloud that behaves as a power law, and you can solve integral equation and get exponent for that power law exactly. It's not too hard. It's a bit cumbersome to explain, so let me skip this. But the interesting, I guess the most interesting thing is that the problem without Aronoff-Bohm flux is not understood, even though I believe that there will be a power law screening cloud when we go in collapsing regime, and then other people believe something else, and there is discussion. Yeah. But in that particular case, you can settle it very, very cleanly. Right. Anyway, so I think I spent too much of your time talking about collapse. Let me stop. Right. So how do you All right, so the next thing I would like to talk about is interactions in graphene, and the topics that I think are of interest to cover is graphene as a model for QED, so we'll talk about that one today, and then analog beta, and then talk about how interactions affect things which we discussed last week, the gap opening in the presence of a substrate. And so how gap or mass is enhanced by interactions. And then talk about various kinds of spontaneous ordering due to interactions, such as excitonic order and superconductivity and else, and then new collective modes. All right. So So for to treat interactions, we should take our graphene Hamiltonian, write it out, and then go to the low energy limit, because, as we discussed, only states near the Fermi level matter. And so in the low energy limit, get a Hamiltonian, which is sum of kinetic energy and interaction energy, and kinetic energy you can write as a sum of Dirac contributions from each Dirac point, and a summation over valley and spin, degrees of freedom. And the interaction term is something like Coulomb interaction and I need to put here charge density. And then this should be normal ordered. N of R is charge density operator. Right.
So it's the long-range part of the slowly varying part of the charge density, because somehow you could have also some.
That's right. So when we derive the low energy Hamiltonian, there are terms which we leave out, and these terms are as follows: in the single particle part, we linearize. That means that the curvature part, or anisotropy, of the Dirac dispersion relation, what's called in the literature trigonal warping, is left out. And then here there are Hubbard type terms, because we when we go to low energy limit, we begin treating position as continuous variable, and in fact it comes from the lattice. And on a lattice, if you look for the difference between the actual interaction and this interaction, there is some Hubbard type interaction that is left out. And so all these bits are small as lattice constant divided by de Broglie wavelength. And so by that parameter we can leave them out. So here I forgot to write the dielectric constant. The dielectric constant will be 1 for a freestanding graphene in vacuum. And then, let's say if graphene is on a substrate, then K would be epsilon plus 1 over 2, where epsilon is dielectric constant of substrate. Right. It's not very important, but just for reference. Right.
In the density, if you start from the lattice model and you express n of r, you have also terms that couple two different Dirac points that corresponds to some fast oscillations. You may say that you can wash them away if you have a slowly,
Yeah. So there are, I mean...
But I don't think it's only terms that give these interactions, because you can have, if you wish, in the Fock terms,
Yeah, of course. So there are many, I mean, Hubbard maybe is a, I mean, you can... Many interaction terms that you can derive, and it can all be found in literature on carbon nanotubes, where I think this was first discussed. That depend on AB sublattice structure and etc. But they are all small in that parameter, and so we're going to leave them out. I mean, they need to be brought in if we discover phenomena that cannot be resolved without these interactions. So if we discover some massive degeneracy that cannot be handled without these interactions, then these terms should be brought back in. But we're not going to talk, at least not today and not next time. We're not going to discuss any of that. Right, and maybe in way of finishing notations, the last thing to say is that this is the massless Dirac Hamiltonian, which is of this form for all valleys and spin components. And if you do a careful derivation, then you find that k and k prime points have opposite signs. But that can be handled, I mean, if you like, it can be handled by relabeling Pauli matrices and in redefining Pauli matrices to absorb minus signs in the Pauli matrices, and then all these single particle terms become identical, which you may or may not want to do, but just a remark. Okay, so what are the properties? The fine structure constant. So basically what I'm going to argue in the next 10 minutes is that this problem is very analogous to QED, to the canonical QED. And in particular, if you take, as we already discussed, the Hamiltonian is scale invariant, and because of that, if you construct the ratio of potential energy to kinetic energy, which is fine structure constant, it will be scale independent in the same way as in QED. QED is also scale invariant in the same way. And so the fine structure constant I can write down as the true fine structure constant times C over V, and so that factor is 300. So this is 300 over 137, and so that's approximately 2.2. So the point is that it's a order 1, and so we have a case of QED at strong coupling. Yes? So the difference from canonical QED should be obvious. This is 2 plus 1 dimensional, and Coulomb interaction is instantaneous. In the real QED, this is 3 plus 1 dimensional, and interaction propagates with the speed of light, the same velocity as massless fermions. However, interestingly, these two differences come to cancel each other, and from field theoretic point of view, we get, because of these two things, we get similarity with conventional QED. And interaction effects are important simply because coupling strength is large. But also just in QED, they can be handled easily, can be handled by perturbation theory. Yeah.
Why QED can be handled by perturbation theory is in real QED alpha is much smaller than 1. But here, since it's in a strong coupling regime, why you can still use
Well, okay, yeah. So we are, it's a bit worse than in QED, in the real QED at weak coupling, but if you think of all other theories, QCD or something else where theory is not renormalizable, or it's renormalizable, but you get some strong coupling. The interesting behavior is the strong coupling behavior that is hard to infer from based on renormalization only. So here, all these problems will not be present, and it will be very much like, except this thing that you said, that coupling strength is stronger, the behaviors will be similar to canonical QED. So, okay, so based on that, I can write down a model, and let me just go here.
Leonid,
Yep.
alpha is not meant to be alpha.
It should, so when we get to the real material on a substrate, we should put kappa in. Also, if you think carefully about what real coupling strength is, there'll be a 2 pi here because of Coulomb interaction form factor, and there'll be also some cases number of flavors. So there may be some dimensional. When we go from fine structure constant, just like in QED, when we go to fine structure constant to calculating some interaction effect, there will be a prefactor, numerical prefactor in alpha. And kappa most definitely will be there. So if I write an effective interaction, so what I typically find is that it's, 2 pi e square over HV, and there is kappa, and also sometimes there is n, number of flavors. Right? But we'll get there. Right. So because of what we said, it's tempting to put everything in a QED-like form. Take 2 plus 1 massless Dirac fermions with 3 plus 1 dimensional instantaneous interactions. And write effective action which will be a sum over n flavors, and then the kinetic energy part will look like this. And coupling to Coulomb potential, I will write down in the canonical form by introducing a gauge field that couples to the time derivative. And so I'll get a term that looks like this. And here, well, let me write the last term and then we'll discuss. And then the Coulomb, the electrostatic potential is three-dimensional, so I'll write effective action contribution, which involves integration over 3D, and then square of that. And then G will be coupling value. Sorry. So this A node is defined as electrostatic, as electron charge times electrostatic potential. Then G square will be 4 pi E square. 4 pi E square. So that this term, this term is just electrostatic energy in 3 dimensions. And then, that's already notation. And then my bar describes standard Dirac conjugation, and my Pauli matrices, my gamma matrices have to obey anti-commutation relations. Canonical commutation relations. This is effective action which is Euclidean, so I already did Minkowski Euclidean rotation from Minkowski space to Euclidean space. And I'm just, trying to bring it to QED, to the form that looks most similar to QED form, and then it will give a nice representation for the discussion. So the choice of gamma matrices may be worth discussing also. We can choose gammas to be Pauli matrices, so 2 by 2 matrices. Sigma 1, sigma 2, sigma 3. And they will obey these anti-commutation relations. And so that's one choice. Then we'll have n equal 4 spin valley degrees of freedom. Alternatively, one can choose 4 by 4. If you don't like this thing that we did here by saying that we'll hide a minus sign in redefined Pauli matrix, if you want to keep the original form of your Hamiltonian, you can do that. But then, in order to account for this minus sign, it's convenient to introduce 4 by 4 matrices that will look like this. There will be gamma node will be sigma 3 . Yeah, I'm doing something wrong here. Gamma node should be sigma 3. This will be sigma 1. This will be sigma 2. So gamma node will be sigma 3 tensor product with sigma 3. And this will be in the valley space, and then gamma I will be sigma I tensor product with identity matrix. right? And in this case, you only sum over spin indices. And this you sum over spin and value indices. So there are two different forms used in the literature, and each of them, they're equivalent, obviously, whichever you prefer. We can pick one and work with it, right? So that's all we need. And then, after you write this effective action, you can look at it and basically read off Feynman rules from this effective action the same way as you do in QED. So, fermion propagator I can write like this, and I will use a 2 plus 1. I will use P that denotes a 3-component vector corresponding to this Minkowski notation, meaning that this is I over P node, P mu, gamma mu, right? Or I can also write it as I over P node, gamma node plus 2-dimensional P times 2-dimensional gamma. Or I can also multiply numerator and denominator by the square of the same thing, and then it will look like IP over P squared. And let's see, so that's my P, and then P squared will be written as a square of time-like component, which is energy or frequency, and space-like component, and here instead of the speed of light there will be Dirac Fermi velocity, which will often suppress and set equal to 1 the same way as in QED speed of light is set equal to 1, but here just for clarity there will be no speed of light here. Instead of speed of light there will be Dirac Fermi velocity, right? And I guess I should also write V for dimensional reasons in this formula.
Excuse me,
right?
Yeah. Say once more this thing with the matrices. I don't understand the dimensionality. You say 2 by 2 when you have 2 by 2.
Yeah. So
4-dimensional.
Right. So this 4 by 4 has nothing to do with Dirac 4 by 4. It's simply I'm simply adding this Pauli matrix to handle plus minus sign in the two values. If you don't like it, just use 2 by 2 matrices and n equal 4 and hide minus sign in redefined spinor components. Okay. In 2 plus 1 dimension, we can deal with everything using 2 by 2 matrices because that's enough to satisfy Dirac algebra. But because we have two cones and k point and k prime point look identical, but if we write down the Hamiltonians, they will have relative minus sign, and so it's convenient to. Sometimes it's convenient to hide this relative minus sign in additional component, but it shouldn't. I don't want to spend time. It's just a convenience, nothing profound in it. Yeah.
In the valley symmetric representation, so once we remove one valley, so we end up with 4x4 matrix.
Yeah.
There, right?
In the valley symmetric 2 by 2.
2 by 2, but if we include the spin, then 4x4.
Or you want to write everything as a matrix? Yes. If you add all these components as a matrix, then there will be 2 by 2 and additional 4 components. So it will be 8 by 8 matrices, but they will be most of them will be identity blocks.
Okay.
Right. So let's not make it complicated. Yeah.
Can you elaborate on how deception works? So A0 is a function of 3 spatial coordinates.
Mm-hmm.
So how do you treat the third spatial coordinate in the first term?
Well, do it just now. That's my... second Feynman rule. Yeah. So this was fermion propagator. And then for a node propagator, we'll have to do what you said. So this describes three-dimensional interactions which are instantaneous. However, we want to eventually go to 2 plus 1 dimension. And since fermions live in 2D, the field, this effective action will define a 2 plus 1 dimensional propagator, which will be simply the three-dimensional propagator integrated over z components. So it will be e square coupling constant and then integral over pz of 1 over pz square plus p square. Sorry, not, should be 4 pi. So this is Coulomb interaction, nothing but Coulomb interaction, Fourier transform of 1 over r, or e square over r in 3D. We need to take it between points which are in a two-dimensional plane, and that means that we have to take this three-dimensional propagator or three-dimensional form factor of Coulomb interaction and integrate over z component. And this p square is a sum of time-like and two space-like components in 2 plus 1 dimension, right? And so if we do that, I mean, the integral is very easy to do because dependence on pz is Lorentzian, and so this is an integral of Lorentzian, and you get you get pi from this integration, and this pi with this 2 pi combined gives 1/2, and so you your propagator will be some number divided by space-like part of your 2 plus 1 momentum. Okay. Finally, the interaction vertex is sorry, I forgot to should get one out here. the interaction vortex is gamma node is arising from this convention. Okay, so the interaction vortex is simply I gamma node, and the interaction strength is absorbed in the propagator. Okay, so these are Feynman rules, and then we can open a QED textbook and start doing calculations, and we discover that indeed it all goes in a very similar way.
Sorry, is it possible to see the gauge field in terms of the original degree of freedom?
So the gauge field, yeah. So let's. So the gauge field that appears here is just instantaneous Coulomb interaction, nothing but that. I could have bypassed this 2+1 representation, 3+1 representation, which I did just to make it QED-like, and I could have said that our Coulomb interaction in 2 dimensions is this, or more precisely, that, right? And so if I take Fourier transform, I'll get a non-local interaction on the plane, which will be instantaneous. So it will be this interaction, and so that the gauge field is just time-like and it's instantaneous. So there's no gauge field dynamics here. Gauge field is electrostatic potential, which is slaved to charges. That's all.
Is it fair to say that you rewrote density-density interaction as a path integral over A0?
Yeah. So I started with path integral, wrote it as an effective action. So that was, I should have said it somewhere here. I take path integral form, write effective action that gives my problem, and in the effective action there is canonical free particle part and also the electrostatic potential outside in 3 dimensions. So it's nothing complicated. I'm just trying to go slowly and make it look like QED. There's nothing profound going on yet, and there won't be.
So, just a question, Leonid. In textbooks, it's usually done in 3+1 dimensions.
Yeah.
And there, the photon has also its dynamics.
Mm-hmm.
My question is that what happens if you do the standard textbook thing, but remove the propagating photon degrees of freedom, and you just purely electrostatics? Does it alter very much the physical conclusions that are drawn usually from incorporating the transverse degrees of freedom of the photon?
You mean stay in 3+1, but make photon instantaneous, right?
Is it known what it does to?
I don't know. There are logs in this problem, so and these logs play out differently depending on. By power counting, what you said will be the same as QED, so it will be logs, but sign of logs may become different, so you can switch from weak coupling to strong coupling. And I don't remember what happened. I'm sure if we spend 5 minutes, we'll figure it out. Let's wait.
Can you explain again why this interaction is instantaneous, and how would it look in normal QED, and why wouldn't it be instantaneous then?
So I think that it will be like what Benoit said. It will be like photon propagator, and in the photon propagator there is 1/c, and if you say that speed of light is infinite in this problem, you kill. So there will be photon propagator. which in 3+1 representation will look like that, or in Euclidean representation like that. And if you say that speed of light is infinite compared to my particle velocities, so that my photons are slave to charges, then simply drop this term. Which is basically what I did already at this stage, but then I also reduced it to 2+1 dimensions, and so that's the result. Okay.
So I suspect that in 2 dimensions there are 2 things that help justifying this approximation. First, the fact that velocity is much smaller than speed of light, and also the fact that you are in 2D, so screening effects somehow are much weaker than 3D as well.
That's right. So because I am on 2D, the photon will go like this, and so it will be long range somehow, even at strong coupling. Yeah. So in fact, turns out that this is exactly what I was going to say. And this is instantaneous. Interaction. Right. And so if we do power counting, if we draw our favorite Feynman diagrams, polarization operator and self-energy, do power counting and vortex correction, do power counting, we'll find that power counting works exactly the same way. You have one space dimension lower, but also one power of momentum lower in the photon propagator. So power counting the same as in QED. As in canonical QED. And because of that, there will be log divergences. And we have to handle these log divergences by introducing cutoff, and there will be a cutoff on. So in our case, there will be a cutoff, UV cutoff on lattice scale. Or in terms of energy, it will be graphene bandwidth. And what we have to analyze is the behavior at low energies. And so from that point of view, this is different from canonical QED, where we know what happens at low energies, but we're interested in whether theory is renormalizable or not at high energies, and we're trying to compute contributions over normalization to physical observables. So a normalization group runs in the other direction. Here it runs from low energies to high energies, here high energies to low energies, and that's known, but let's just write this down. So here we have running UV cutoff. And things of interest is renormalization of observables. Mass, G factor, charge, etc. Scattering matrix. Okay. So, time to stop. Right. Give me. I mean, we prepared grounds for what we're going to do, so that's good. Let me just, in way of overview, let me just say what's going to happen next time when we will look at these diagrams, and you're welcome to try it yourself. So if we do perturbation theory, there are two ways to do perturbation theory. One can either treat coupling as weak, and so this is, take fine structure constants, say it's much smaller than 1, and then we should be able to extract log divergences from these diagrams and then sum them up in RG fashion. One can also, there's another way here, which is take the number of flavors as a parameter and take a large n limit. And so both of these approaches require, after you calculate it, require continuing result to physical values. So you have to continue to alpha over the 1 in the first case. In the second case, your k, if you take n to be large, you can take alpha to be over the 1 and you still have a good theory. So you have to continue, but then you have to continue to n, which is 4 or 2, depending on whether you're using 4-component fermions or 2-component fermions, right? And so that's point number 1. Then point number 2 is that you can look at these 3 diagrams, and what you find is that pi is non-divergent, same as in QED, and in fact you find that pi of q is some number times q q modulus, and a number we can compute tomorrow. Then if you look at self-energy, find that self-energy is log divergent and at leading logarithmic order behaves as e square over 4 times log of the cutoff ratio times gamma p. And I guess there is a, that's right. And so also vortex correction is non-divergent. So these are, results I'm showing here are for weak coupling, right? And so what you conclude when you do this calculation is that you get, because of interactions, you get a logarithmic renormalization of the space-like part of the propagator, and that means that you get an increase in Dirac Fermi velocity. So this term looks exactly like my term over here, except that instead of v, I get e squared over 4 times a log. And so when I ask what will happen if I if I integrate scales one by one, going from UV to a smaller scale, then from a smaller scale to still smaller scale, so we eliminate shells in the energy momentum space one by one, I will get, from each shell, I will get an additional correction to Dirac Fermi velocity, and it will go up, right? And so from that, we will see, because there is no log normalization here and here, self energy is the only contribution that renormalizes. A very simple analysis shows that Fermi velocity goes up, and so instead of Dirac cone, you get a Dirac cusp. You get something that looks like Dirac cone at high energies, but then it becomes steeper and steeper at low energies and turns into this. And so we'll look at this next time, and then also discuss extension to larger limit. But comparing to canonical QED, this means for fine structure constant, it means that fine structure constant flows to weak coupling, and so that's the same behavior as in canonical QED. So indeed, this model not only superficially but physically models the behavior in canonical QED. And so, more on that later. All right, so sorry for going over time.